Okay, in this video we're going to look at binomial probabilities, and a binomial situation is a pretty important discrete random variable. And there are four conditions to recognize a binomial situation for a random variable x. Okay, and you can read those up here. Okay, the first thing is there's a fixed number of trials, n. Okay, so for example, you may flip a coin 10 times, you may spin a spinner 6 times, and so on. Okay, so there's a fixed number of trials. Number two, there's only two possible outcomes for each trial, success or failure. Now you need to define what you're going to say a success is. So if you flip a coin, you might say flipping a heads is a success. If you spin a spinner that has different colors on it, you may say getting a red is a success. If you roll a die, you may say rolling a 4 is a success. That means everything else would be a failure. Okay, so you define what a success and failure is. Okay, the third thing, the probability of success is p, and the probability of a failure is 1 minus p. Fourth thing, the trials are independent, which means p and 1 minus p remain the same for each trial. Okay, so we'll look at a few examples here and determine whether or not we have a binomial situation or not. Okay, so in order to be binomial, it must satisfy each of the four rules up here. So part A, we flip a coin until you get a tails. Okay, is that binomial or not? Well, let's go through. Are there a fixed number of trials n? Well, I would say no, because if you flip the coin once, you may get a tail, you may not. You may have to flip twice, 3 times, 4 times, 5 times. There's not a fixed number of trials, so that one, right off the bat, it violates the first rule. Okay, there are not a fixed number of trials. B, flip a coin 7 times. Let x represent the number of heads. Well, if we flip a coin 7 times, now there is a fixed number of trials, so 1 is satisfied. 2, there are only 2 possible outcomes for each trial, success or failure. Well, if you flip a coin 7 times and x represents the number of heads, you can say getting a heads is a success, getting a tails or not heads would be a failure, so that's okay. 3, the probability of success is p, failure is 1 minus p. Well, if you flip a coin, the probability of getting a heads is 1/2. Not a heads or a failure, 1 minus p would be 0.5. And they are also independent because those probabilities do not change from trial to trial. So D would be yes. Part C, choose 3 cards from a deck without replacement. Let x be the number of hearts. Well, if we choose without replacement, there's a fixed number of trials because you're choosing 3 cards. But when you do this without replacement, they would not be independent because you're not putting the card back, so that means the probabilities change. You could classify a hearts as success and everything that's not a hearts as a failure, but they're not independent, so no, the fourth rule, okay, because the probability will change because of without replacement. Okay, and then part D, well, now we're doing the same thing, except we're doing it with replacement, so that takes care of the independence issue from number 4 in the previous example. Okay, so that one would be yes. Okay, so moving along, that's how you recognize a binomial situation. Okay, and then what we're going to look at is if you have an example. And this is meant to be a fairly basic example, but I think it'll hopefully make sense. Okay, suppose there's a game. Okay, there's a game and a spinner has red, blue, green, yellow, orange sections of equal area. A success on a spin is if it lands on red, and you're going to spin the spinner 4 times. Okay, so we're classifying a success as spinning a red. That means everything that's not red will be considered a failure. So to verify this is a binomial situation, well, we have a fixed number of trials, 4. Okay, so I'll just go right here, n equals 4. Okay, so we have a fixed number of trials. Do we have 2 possible outcomes for each, success or failure? Well, we just said success is spinning a red, and a failure will be anything not a red. So the second condition was satisfied. Third condition, can we find the probability of success? Well, P, the probability of spinning a red on any individual spin will be 1/5, which you can also write as 0.2. And then a failure, 1 minus p, that probability would be 4/5, which is 0.8 as the decimal. And the trials are independent because when you spin, you're going to assume that each spin will be random, and whatever you got on the previous spin does not affect what you get on the next spin. Okay, so it is a binomial situation, and there's your NP and 1 minus p. Okay, so the next thing we have to look at is list all the possible sequences of obtaining 0, 1, 2, 3, and 4 red outcomes. Now we should recognize that if you look at this as what can happen when you spin that spinner 4 times, you could get 0 red, you could get 1 red, or you could get 2 red, or 3 red, or 4 red. Those are the only possibilities. If you're looking at getting reds, you can either get 0, 1, 2, 3, or 4 reds, and that's all that can happen. It doesn't matter if you get, say, 1 red, 1 blue, 1 green, and 1 yellow, because you're looking at this as red is success, not red is a failure. So when you list the possible sequences of obtaining 0, 1, 2, 3, and 4 red outcomes, getting 0 red, we have to look at, well, how can that happen? Well, in order to get 0 red, that means you have to get not red in the first, second, third, and fourth spin. And I'm going to use N, okay, like capital N, to represent not red. Okay, don't confuse it with lowercase n, the number of trials. Okay, capital N just meaning not red. So in order for that to happen, the first spin had to be not red, second, third, and fourth had to be not red also. It doesn't matter if the not red was an orange or a green or a blue. It just mattered that it was not red. Okay, that's the only way you can get 4 not reds. Okay, or 0 reds. So there's only one sequence of getting 0 red. Okay, then we look at getting 1 red. Well, you could get the first one as red, and then the next 3 would have to be not red. Or you could get not red first, and then red second, not red, not red. And basically you move that R through to the next space, and if you do that, okay, you see there are 4 sequences of that. Okay, in order to get 2 red, let's just suppose you got red on the first and red on the second, then the next 2 would be not red. Or you get red on the first, not red on the second, red on the third, not red on the fourth, and so on. And just for the sake of time, rather than me writing all this out, okay, and explaining all that, hopefully you get the idea now. Okay, what I'll do is I'll go to my other sheet of paper that I have this all filled out on, and those are the possibilities. Okay, so if you need to pause the video and think your way through that, okay, feel free to do that. Okay, but I'm going to move on to the next. Okay, so now we're going to fill in the following chart. Let random variable x, okay, RV stands for random variable x, represent the number of red outcomes. Okay, so what we're going to do is we're going to fill in this table. Okay, let x, random variable x, is the number of red. Well, we could have either 0 or 1 or 2 or 3 or 4 reds. Those are the only possibilities for the number of red spins. The number of sequences. Well, to get 0 red, there's only one way that could happen up here, which was getting 4 non-reds. Okay, so that is going to be 1. Okay, there's only one way for that to happen. Okay, and then in order to get 1 red, there were 4 ways. Okay, the 4 ways were up here for 1 red. And then for 2 red, there were 6 ways. 3 red, there were 4 ways. And then 4 red, there was 1 sequence, or 1 way. Okay, which was over here, 4 R's. Okay. All right, so each of those number of sequences represents the number of ways we could get 0, 1, 2, 3, or 4 reds, okay, for each of those cases. Okay, so now what we want to do is we want to find the probability of each sequence. Okay, so now we know how many ways we could get 0 red. What is the probability of that happening if you spin the spinner 4 times? Well, when you look at getting 0 red, the probability of the first one being non-red was 0.8. The second one being not red was 0.8. The third one being not red was 0.8. And the fourth one being not red was 0.8. So when we look at not red and not red and not red and not red, what we do with ands is multiply them. Okay, and that's back from the probability chapter. Okay, when you have and, you're going to multiply. So this will be 0.8 multiplied together by itself 4 times. So that would be 0.8 to the 4th. Okay, so the probability of getting 0 red is 0.8 to the 4th, which if you put that in the calculator is 0.4096. Okay, for the next possibility, for getting 1 red, there were 4 sequences. So if we look at the sequences up here, the first one being a red, that probability was 0.2. These other 3 probabilities for not red, each of those was 0.8, and we had 3 of those, so that would be 0.8 to the 3rd. The next one, the second red again was 0.2, but then again notice we have 3 ends, which again will be 0.8 to the 3rd again. Okay, so you can look at each of those sequences, and you're going to have 3 ends. So you're going to have 0.8 to the 3rd each time, and then 1 red probability was 0.2. So we're going to have, 0.2 once and 0.8 3 times. Okay, that 0.2 represents 1 red, and the 0.8 to the 3rd represents 3 not red. Okay, and as you work your way down this, okay, we notice in the next one, okay, sorry, I'm trying not to have it too overwhelming here. Okay, the next one, there were 6 ways to get 2 red. So when we look up at the top here, red, red, not red, not red, what you would have is you would have 0.2 twice and 0.8 twice. The next one, 0.2 twice again for the 2 reds, and then 0.8 twice for the 2 not reds. Okay, so each time, for those 2 reds, you're going to have 0.2 to the 2nd, and then 0.8 to the 2nd. Okay, multiply that together, 0.0256. Okay, so the probability of getting any one of those sequences of 2 reds is 0.0256. And there were 6 ways for that to happen. Okay, and if you go in the similar pattern to find each of those probabilities, okay, there you have it. Okay, 0.2 to the 3rd, basically saying there were 3 reds and 1 not red. And then in the last row, 0.2 to the 4th, basically saying you had 4 reds, and the probability of each red was 0.2. So raise 0.2 to the 4th, you get 0.0016. Now, what's essential to understand here is to recognize that this column represents the probability of each sequence. So 0 red could only happen one way. So the probability of exactly 0 red is 1 times that sequence, 0.4096. The probability of 1 red, well, 1 red could happen 4 different ways. So you multiply this sequence, the probability of that sequence, by 4 to get the probability of 2 red. I'm sorry, I just said that wrong. To get the probability of 1 red. Okay, there's 4 sequences. The probability of each sequence is 0.1024. So basically multiply those and you get 0.4096. So the probability of 1 red is 0.4096. Now it just so happens that these work out to be the same. That's just with the numbers that we had in this one. That's generally not true. To get probability of 2 reds, there were 6 ways, or 6 sequences, to get 2 reds. Each sequence had a probability of 0.0256. The 6 ways for that to happen, multiply those together, 0.1536. Okay, and then you could fill in the rest. 4 ways to get 3 reds. Each sequence had a probability of 0.0064. And then 1 way to get 4 reds, and each sequence had 0.0016. Okay. Now what you might notice is the only possibilities of the number of reds were 0, 1, 2, 3, or 4. So that means when you take the probability of exactly x reds, nothing else can happen except 0, 1, 2, 3, or 4 reds. Add these probabilities up, and you will get 1. Okay, if you don't believe me, go ahead and do it. Okay, then at the very bottom of the page, I ask you a few very basic questions. Find the probability x equals 2. That's basically saying find the probability of rolling 2 reds. Well, 2 reds, okay, exactly 2 red, is 0.1536. The probability x is greater than 3, which is basically saying the probability that the number of dots is more than 3. Well, the only possibility there is 4. Okay, so 4 is more than 3, or greater than 3. So that's 0.0016. The probability x is less than or equal to 4 is saying the probability you get less than or equal to 4 red dots. I'm sorry, 4 red spins. Okay, that would be a total of 1. Okay, so you get 0, 1, 2, 3, or 4. And you would basically saying you add all these up, you get 1. Okay, on the next page, find the probability of at least 1 red in 4 spins. So at least 1 red could be 1, 2, 3, or 4. Okay, so you add those up, 1, 2, 3, and 4. So you're going to add up the 0.4096, 1536, 0256, and 0016. Add those together, 5904. You could also use a complement. At least 1 red, its complement would be 0 red. So you could do 1 minus 0 red. So 1 minus 0.4096. Okay, next one, probability of less than 2 red in 4 spins. So less than 2 could be 0 or 1. So you're going to add up the probability of 0 plus the probability of 1, and that'll give you 0.8192. Okay, so filling in a table like that takes a little bit of time and understanding, and it's not an easy thing. Okay, but there is a general formula that we're going to be able to use. Okay, and also we're going to be able to use our calculator, so that'll help us also. So using our answers to number 2, develop a general formula for a binomial situation. Okay, so when you look at the probability of exactly x successes and n trials is p of x equals what? So if you think about how we generated the table up here. Okay, what we did, we took the number of sequences, or the number of ways to get 0 red, the number of ways to get 1 red, 2 red, and so on. And then we multiplied that by the probability of each sequence. Okay, so the number of sequences, this is not obvious, but if you go back to chapter 4 with combinations, another way to count the number of sequences, or the number of ways you can arrange 0 reds, 1 red, 2 red, 3 reds, or 4 reds, if you choose 4, so we had 4 spins, is NCX. Okay, so NCX will tell you the number of ways you can arrange X red spins. So for example, if you did N is 4, because we have 4 spins, X will be the number of successes. If you did 4C2, okay, so 4C2, it will give you 6. If you did 4C3, that'll give you 4. 4C1 will give you 1. Okay, so that's the first thing we did, we found the number of sequences. So rather than listing them all out like we did up on top there, rather than doing that, the quick and dirty, or quick and easy way to do that, 4C0, 1 red, 4C1, 2 red, 4C2, 3 red, 4C3, and 4 red, 4C4. And if you do that in your calculator, and I'll show you how to do that in a minute, you will get each of those number of sequences for the number of red. Okay, so moving along here, so trying to take too much time. So we know the number of sequence of each is NCX. And then what we look at is when you go to that table, okay, sorry, I keep moving around here. Okay, when you go to that table, we notice that we have 0.8 to the fourth for 0 red. And then the next row has 0.8 to the third, 0.8 squared, 0.8 to the first, and then there's no 0.8. And then notice what happens with the 0.2s. For 0 red, we start off with 0.2s, and then for 1 red, we have 0.2 to the first. For 2 red, we have 0.2 squared, and so on. So the probability of each sequence, okay, you're basically looking at P to the X. Well, P was the probability of a success. So when you look at 0.2 to the first, that meant you had 1 red. Well, notice we had to multiply that by 0.8 to the third. That would be 1 minus P to the n minus x. So if x was 1, n is going to be 4 every time in this example. 4 minus 1 will give you 3. So we had 0.2 to the first, and then 0.8 to the 4 minus 1, or 0.8 to the third. Okay, so that is a formula for a binomial. So basically what happens is the way you look at it, you have n trials, in this case 4. You want to choose how many successes, how many reds. So if I were to say 4C3, that would mean in those 4 trials I want to have 3 reds. The probability of a red is 0.2, and you want 3 of them. The probability of not a red is 0.8, and you would have to have 1 of those. So notice the exponents, 3 and 1 will add up to 4. Okay, so that's the kind of the easier way to look at this formula. It looks kind of confusing, but it really isn't too bad once you practice a few of them. Okay, so if you want to take a minute and use the formula to check some of those answers in your table, you can go ahead and do that. Okay, I'm going to show you using your calculator the way you can get the probability of exactly x successes in n trials. Okay, so I'm going to go to the calculator. Okay, and suppose we want to find the probability of 0 red. So P of 0. Well, I'm going to do binom PDF, and the way you get to there is you do second vars. See how it says distribution above it? Okay, hopefully you can see that. Okay, and what we're going to do is we're going to scroll to binom PDF. Now notice there's also a CDF, which we'll get to in another lesson. But binom PDF, oops, I forgot the F on here. Okay, means the probability of exactly X number of successes. Well, there were 4 trials. The probability of success on any one trial was 0.2, and you want 0 of them. So we choose binom PDF, and then 4, comma, 0.2, comma, 0, and that gives us 0.4096. And if I go back to the table, that was that first row there, 0.4096. Okay, that's this probability right here. Okay, the next one, if I want to find the probability of exactly 1, we do binom PDF 4, because we have 4 success and we want 1 success. So again, that will be binom PDF, so second vars, binom PDF 4, comma, 0.2, comma, 1. And that was 0.4096, which is the second row in the table up here. Okay? And you could do that for each of these, but I'm not going to waste the time and do that anymore. Okay, so that is where the binomial formula comes from. Okay, so this formula right here is going to be important. Okay, and usually if you think your way kind of common sense through it, then it isn't too bad to memorize. People always get upset, oh, I got to memorize that formula. Well, it's not too crazy to memorize that. Again, when you look at what I wrote here, the 4C3, there's 4 trials. You want to choose 3 successes. So probability of success in any single trial is 0.2, and you want 3 of them. Not a success, the probability is 0.8, and you need 1 of those. Okay, so I think it's easier, kind of common sense to look at this formula rather than looking at all the n's and x's. It can be kind of confusing.